All right, folks, back at it. Okay. All right, we can have that soul shakedown party all night, but we got to do some chemistry instead. So here we go, picking up right where we left off. So that last video was a little bit longer than I wanted it to be. It was right around 45 minutes. So this one should be fairly short. In my experience with this next subject on precipitation reactions, this can be a really challenging subject for students. And a lot of it is because of dealing with these formulas. So if you recall last week before the exam in our discussion worksheet, I had you really work on breaking apart chemical formulas into their respective ions, so particularly ionic compounds. So if you're still struggling with that, that's a really good exercise to practice because for this next bit on precipitation reactions, you have to be really comfortable with breaking apart those ionic compounds into their two respective ions. Okay, so what is a precipitation reaction? So let's talk about that. Okay, so you can see here I've got potassium chromate, right? And as a reminder, when this breaks up into its respective ions, we get two potassiums, okay, and those are aqueous, plus a chromate, right? And you can see that picture right there, right? Two potassiums for each chromate. And as it turns out, chromate, the chromate ion, is kind of a yellow color in solution, okay? So we want to start using our powers of observation in chemistry, particularly in precipitation reactions, okay? So barium nitrate, right, when this thing breaks up, it becomes a barium, and remember that's 2 plus, so that means we need 2 nitrates for each barium, and you can see that right here, okay? There's the 2 nitrates and there's the 1 barium. Okay, so in the reaction, right, this is one of those double displacement reactions that you talked about in your lab. And so what's going to happen when I combine these two things, there's going to be an exchange of ions, all right? And the way we know that is because here is a picture of what happens when you can tell that this is the potassium chromate getting poured into the barium nitrate, because again, we noted that the potassium chromate is yellow. So the potassium chromate has to be there, and we're pouring it into the barium nitrate. And look, see all this cloudy stuff right there? That's what we call the precipitate. And those are the solids, okay? So in this ion exchange, what is happening is now our potassiums, so they were with the chromate, right? But now each of these potassiums are going to react with the nitrate, or the nitrate's going to react with the potassium, either way, right? We'll just say they both get together. And the other possibility is for the barium and the chromate to get together. So this is that ion exchange, that double displacement, all right? And what we have to figure out is what is the precipitate, so what is the solid, and what is in the supernatant. And in the supernatant, that are the supernatant represents the solution that's surrounding the precipitate. And that supernatant will contain the aqueous spectator ions. So how do we know which one is the solid? Our options are either barium chromate, so let's write that for our product. So our product could be, right, because you notice, like if I just said the product is potassium chromate, that means nothing happened because potassium chromate was a reactant, okay? So my possibilities are barium chromate or potassium nitrate. So one of those will represent the precipitate, which is the solid. The other will represent the ions that are in the supernatant. And we have to use what's called the famous solubility rules to figure that out, okay? So I'm not going to make you memorize these solubility rules. You will be given these on an exam, or you'll be able to reference these, but you do have to know how to use these rules, okay? So we have two separate charts. We have the soluble chart, and we have the insoluble or slightly soluble chart, okay? Soluble means it completely dissolves, completely, and don't mix that up with completely ionizes, okay? Because it does completely ionize and it completely dissolves. Slightly or insoluble means there's solid chunks left over, and those solid chunks are the precipitate, okay? So look at the rules here. So soluble, most salts with nitrate or acetate, no exceptions to the rule. And so keep in mind, when there's exceptions on the soluble chart, that means it's insoluble. And when there's exceptions on the insoluble chart, that means it's soluble, okay? So for example, when I look at this and I can see most salts with nitrate and there's no exceptions, that means if something has nitrate in it, it's going to completely dissolve, meaning it will be soluble. So what does it mean to have an exception? Well, here we go. Let's play with this one, okay? Most salts with chloride, bromide, or iodide. So for example, NaCl, sodium chloride, will always be soluble. So it will completely dissolve. But what about silver chloride? Silver chloride will be insoluble or slightly soluble. And so what that means is silver chloride will make solid precipitates. It'll make solid chunks, okay? So let's go back to this now. And we remember that when I was doing this reaction here, okay, let me see, what is my next slide after that? Yes, so let's write this out. So good practice to break this down, right? 2K plus AQ plus, I know I did this already, but this is good practice all the same, okay? And then now this breaks down into barium and 2 nitrates. So remember, this is why I had you practice that on that discussion worksheet. Get good at breaking down these formulas and recognizing the difference between coefficients and subscripts and what those things tell us, okay? So now I can see my options were either to combine potassiums and nitrates, okay, or barium and chromate. And now when I look at that solubility rule, most salts with nitrate are soluble. Okay, so what that means is when I combine these to make KNO3, it will be aqueous. There has to be 2 of them, right? Because there was 2 nitrates, 2 potassiums. I know that you want to write this K2, NO3, 2. Don't do it. Don't do that. That's not correct. It's 2 KNO3, aqueous. And then now when I look at, well, what about the barium and the chromate? I don't see any chromate. Here is chromate on the insoluble list, and I don't see barium as an exception. So that means those solid chunks that we saw had to be barium chromate, and that makes sense. So this is the precipitate. And that makes good sense because we remembered from the picture, I told you that chromate is yellow. And look, our precipitate is a yellow color. So it had to have the chromate in it. Of course, that's assuming that you knew the chromate was yellow, but if you didn't know that, now you do. And also, now we can see how our powers of observation, our ability to logically deduce what the product has to be, is also present in our deciding what is the correct product. Okay. Okay, so now let's summarize what we've got here. So the way I've written this all down, and notice here we have to put a solid there to indicate that that's the correct product. Okay. So that's our precipitate. This is the full formula reaction, all right, where I've got all of the formulas put together. Okay. So now when I break it apart into its ions, and look what happened to the potassium chromate, right? 2K plus Cr42 minus. And then the barium nitrate was breaking apart, Ba2 plus 2NO3 minus. Okay? That's the complete ionic equation. But check out the product side. The precipitate is not an ion, it's a solid. So it stays together in this reaction. And now we noticed here, the KNO3, it's aqueous, okay? So that means it is also going to be completely broken apart. And look, 2KNO3 becomes 2K plus 2NO3 minus, okay? And now finally, to get to the net ionic equation, let me show you a cool trick you can do, okay? Because in math, as well as chemical reactions, if the left side equals the right side, then they cancel out. So check it out, 2K plus and 2K plus, they're gone, okay? And 2NO3 minus and 2NO3 minus, those are gone. But I can't cancel the barium ion and the chromate ion because chromate aqueous is not the same as chromate solid. And then now look what happens. What remains when I do this process is the net ionic equation. The net ionic equation, look, all the spectator ions are gone. And now we only see what I like to call the action. The net ionic equation tells us the action that happened. It tells us about the chemical reaction that took place. Okay? So I know I don't have the learning goals up right now, but this is definitely a learning goal to be able to do all three of these things. Be able to comfortably write all three types of equations, the formula equation, the complete ionic equation, or the net ionic equation, okay? And you can see that really, if you start with the formula equation and you feel pretty good about that, you can work your way through the complete ionic as well as the net ionic. But our goal for you is to be able to just look at a precipitation reaction and get the net ionic. So I'm going to write this down as an eventual goal, be able to just look at a formula equation and come up with the net ionic. Okay? So I know that's going to take you some time. It's going to take some practice, but that is a good goal to work towards. And I'll show you how I kind of look towards this. So when I'm viewing the formula equation, okay, oh yeah, I can see barium chromate as the solid. And so what I like to do is write that down as the product, and I'm going to work backwards. Okay, so I know that's my solid. All of this aqueous stuff, they're all just going to become spectators unless they're part of this solid. So now that means in quickly scanning this formula equation and working backwards, I say, how do I make barium chromate solid? Well, I can make it from a barium 2 plus aqueous and a CrO4 2 minus aqueous, okay? So that's your goal, is to be able to quickly, like that, come up with a net ionic equation. So obviously you're going to have to spend some time practicing the solubility rules. Okay, I don't expect you to memorize them. You'll be able to have them in front of you. But particularly if you already have the full formula equation and you already know what the solid is, then I want you to be able to come up with this net ionic equation like that. Okay, that's your goal. Okay, moving forward. So I have one example problem to work through here. Let me see what the next slide After that is yes. Okay, so just one example that I'm going to go through, and one more brief slide after that, and then that'll be done for this video. Okay, and so this is going to be good practice because this is going to give us not only practicing the solubility rules for this problem, but also doing a limiting reagent problem, because believe it or not, this is actually a limiting reagent problem. So let's see the problem. It says, when aqueous solutions of sodium sulfate and lead nitrate are mixed, a reactant precipitates. Okay, stop. I'm not even going to read anything more. I can see that I don't have a reaction, so I have to get a reaction out of this. So it says, when aqueous solutions of sodium sulfate and lead nitrate, so this is actually lead 2 nitrate, mix, okay, a precipitate forms. We have to figure out what that is, okay? And what I can do here, because I'm working on the full formula equation, I can automatically see that it's going to have to either be lead and sulfate or sodium and nitrate. Okay, so I'm going to write that down in pen, a different color, right? I'm going to exchange the cations and anions. So there are my options as to what is going to be the possible product. And right away, I'm just going to go ahead and write those down. And so I remember that sodium is +1 and nitrate is +1. So that becomes NaNO3. But I can see that I have 2 sodiums here and 2 nitrates here. So I'm going to put a 2 right in front of there to balance. And I'm not sure what the phase of that product is yet, if it's aqueous or solid. And then my other option is lead and sulfate. So from this formula, I can tell this is lead 2+, and I know that sulfate is 2-, so that's going to be PbSO4. And I'm not sure what the phase of that is either. So let's go back and look at the solubility rules, okay? So, I remembered my rule for nitrate, that basically everything with nitrate is soluble. And then I can see, oh, here I have sulfate, and sulfate is supposed to be soluble except when paired with lead. Okay, so lead sulfate is an exception on the solubility chart, on the soluble chart. That means it's insoluble, and insoluble means this is the solid, and the sodium nitrate are the spectator ions. Okay, so this is the product that we're interested in. And so now the problem tells me, calculate the mass of reactant formed. Okay, so how many grams of the lead sulfate when 1.25 liters of a 0.05 molar lead nitrate solution and 2 liters of a 0.025 molar sodium sulfate solution are mixed. This is how I know that this is a limiting reagent, because I've been given amounts of both reactants. So now I'm going to erase this red ink right here, because now I'm going to put different information there, okay, to tell me, to kind of help me guide my calculation. Okay, so this is what I'm trying to do. I'm trying to get to grams of lead sulfate, and I know that I have 1.25 liters of a 0.0500 molar solution of this, and 2.00 liters of a 0.250 molar solution of this. And just like my true limiting reagent style, first I'm going to do one calculation, right, starting with the lead. And then I'm going to do a second calculation, starting with the sulfate. And we remember that the least is the most, okay? So let's get that going. I'm going to say number 1 here, number 2 here, and let's do it, okay? And so I also remember, hopefully I remember, that when I have a volume and a molarity, I don't need the molar mass. So remember, when I have volume times molarity, it directly gives me moles. So I don't need the molar mass of any of these things, which is great. Hallelujah. Okay. So now I'm going to start by saying 1.25 liters of the lead nitrate. Okay, and remember how I can use this molarity. Remember, 1 molar means 1 mole in 1 liter. Well, I don't have 1 molar, I have 0.05 molar. And so what that means, in 1 liter of this solution, I have 0.500 moles of lead. And I'm just going to write Pb2 plus because really that's the stuff that's reacting. Okay, we could have wrote lead sulfate there and that would have been okay. But I recognize that it's really the lead that's important. And in this reaction, it's 1 mole of lead makes 1 mole of lead sulfate. 1 mole of lead nitrate makes 1 mole of lead sulfate. So I can say now 1 mole Pb2 plus makes 1 mole of PbSO4. Oh, I ran out of room here with my red arrows. And then now, because it's asking me to calculate the mass of precipitate, I need the molar mass of the PbSO4, okay? I need that molar mass. And I did that already. It's a pretty heavy sucker. I just did it to 3 sig figs. 303 grams of lead sulfate in 1 mole of lead sulfate, okay? And so when I do that, the answer I get is 15.2 grams of lead sulfate, starting with the lead, okay? So now let's start it with the sodium sulfate solution instead. So I'm going to start with the 2.00 liters. I recognize in 1 liter of that solution, there's 0.0250 moles of sulfate. So sulfate is the important ion. That's the one that's reacting. Okay. And then in this reaction, it is still a 1-to-1 ratio, right? So that's cool. So 1 mole of sulfate makes 1 mole of lead sulfate. And then now I can copy that very last line because I know I need to convert it into grams. And so I just use the molar mass of lead sulfate, 303 grams per mole. And when I do this calculation, so I've got them all written down. So I'll go ahead and calculate them out since I got my calculator. Let's do this top one. So I was just kind of using my cheater notes, but you can see now where I get these numbers. 1.25 times 0.0500 equals, and then times 303. What did I do wrong? Did I write down? Oh my goodness. Okay. So yes, this is why I should do this, because you can see that I copied down the wrong answer. So this one is 18.9 grams. And what do you want to bet that this one's going to be the 15.2? Okay, so now let's do the number 2, okay? So 2.00 times 0.025 equals, and then times 303 equals, haha, that one is the 15.2. Good thing I did the calculation. Okay, so that means this is the most amount that can be formed, which of course means our sodium sulfate was limiting, meaning we would have excess lead nitrate reagent. Okay? So, and just kind of, again, reiterating, this is the important thing. What's going on is being able to use this solubility chart as well as being comfortable breaking up these ions into breaking up these compounds into their respective ions and then forming new compounds by doing that double displacement, by exchanging cation and anion. So if you're still not so comfortable with this, this is a great place where you need to be practicing to get good at these precipitation reactions and, I wanted to say, and the net ionic equations. Yes, and being able to, as this eventual goal, get the net ionic equation. Okay. So the last thing that I'll say is, what does it mean to be saturated? Okay. So we noted that NaCl is soluble because on that solubility chart here, right, there's chloride. Sodium is not an exception, so sodium chloride should be soluble. However, the solubility of everything has a limit. So let's say that solubility has a limit. So you can't put an infinite amount of sodium chloride in water and dissolve it. So for example, seawater is about 3.3 grams of sodium chloride per 100 milliliters. We could also convert that into a molarity if we wanted to, right? By converting, the grams of sodium chloride into moles and the 100 milliliters into liters. Let's just do that really quick. Why not? 3.3 grams of NaCl. So let's see, quick math. I think it's 58.1. So it's 23 plus 35.45, 58.45. 58, let's just say 0.5 grams of sodium chloride in 1 mole. So 3.3 divided by 58.5 gives me 0.056 mole. And that's 100 milliliters. So if I now divide that by 0.100 liters, okay, then I get, let's see here, 0.56 molar sodium chloride in seawater. And you notice when you look at it, that was the wrong color arrow to use. You notice when you look at this, it's homogeneous. Okay, so you, just by looking at it, you would have no idea that there's salt in it, right? It looks like one continuous fluid solution, okay? Or it just looks like pure water. So now look at this. Here's 35.9 grams of sodium chloride per 100 mils. So nearly 10 times that amount. And if I convert that really quick into molarity, I'm not going to show the work here, but I'll use my previous calculations. Okay, so this is 6.1 molar. So that's more than 10 times concentrated. And we can say definitively this solution is saturated. And I know that it's saturated because look, there's solid chunks. There's like a layer of solid NaCl below. And if you notice this cartoon, what the cartoon is showing you is, here is our salt crystal, like our little cube of salt, and some of it is still remaining as a solid, chunk, a salt crystal, and some of those ions are, in this complicated thing that we call equilibrium, where they're precipitating and dissolving, and precipitating and dissolving. The important point being, the supernatant of the solution is 6.1 molar NaCl, and any amount of sodium chloride we continue to add to this saturated solution will result in precipitation. Even though sodium chloride is soluble, that solubility has a limit. So just recognize that not everything is infinitely soluble. You can only dissolve so much before it crashes out of solution, is what we call it, or precipitating. Okay. And in Chem 110, we will explore the quantitative calculations of saturated solutions in much more detail. For now, I just kind of want you to be aware of what a saturated solution is, and be able to use those solubility rules to predict what a precipitant will be from one of those double displacement reactions. Okay, folks, I think that one was much shorter than the previous one. So that's a good place to leave it off.